Now let's take a look here at example number 1. In this question, we're going to be asked to find the exact surface area of the figure that's obtained by rotating the curve y equals x cubed, where x ranges from 1 to 2, around the x-axis. So I'm going to start by going ahead and drawing out a quick picture here of what exactly it is that I'm working with. Again, since x is only going to occur from 1 to 2, I really only care here about my first quadrant. So I know that my x cubed curve looks something like this. It comes up, hits my origin, and then kind of extends out this way. Now I'm going to suppose that 1 exists right here and 2 exists right here. And so I can see that this is the portion of the curve, again, that I'm going to be attempting to deal with. Just this portion right here. Of course, I know that if I'm at x coordinate 1, I'm at y coordinate 1. And if I plug in 2 for x, I'm up at 8. Now I also want to be able to see here what it would actually look like if I was to go ahead and revolve this around the x-axis. If I was to go ahead and revolve this, I can see that I would end up with a picture. It's going to look something kind of like the following. Again, I'm just going to try to repeat the ideas that we did back in the early sections of Chapter 2, which was to take my curve, create a mirror image duplicate on the other side, and then play this game of kind of connect the dots. Notice here, though, I'm not going to actually connect that many dots here. It's kind of just the ends, because what I'm really interested in, again, is how much paint ultimately is it going to take to kind of imagine painting the outside of this figure. Now, I have that surface area formula that we came up with in the last video, but again, remember that that had some important conditions. To use this surface area formula when rotating around the x-axis, or when rotating around the y actually, but I had to have a function that was non-negative and had a continuous first derivative. So I'm going to check those right away. This is not an option, this is a must. So let's see. I'll start by saying we see that y equals x cubed is non-negative on 1 to 2. I mean, that's pretty obvious, right? Because it only creates y values from 1 up to 8. I never hit a negative. Okay, but also we could probably see here that y prime is 3x squared, and that's a polynomial. Remember, polynomials are always continuous. Oops. So I can say that's definitely continuous on the interval from 1 to 2. So because I meet both of these conditions, I now know that the surface area that I can set up here is able to be, or I can set up my surface area using the integral that we established above. If these conditions weren't met, I may or may not be able to use this integral. I don't really know. So notice that since I'm revolving here around my x-axis, I can see that I'm going to have frustums, again, that line up horizontally. And so because of this, I can imagine that their radii are measured in a vertical sense, and that this is going to be a dx question by default. So I'll start by setting up my arc length piece at the back. My arc length piece is 1 plus my derivative being squared, and I know that I integrate from 1 to 2. I also know that in the front I'm going to have a 2 pi, and remember here I should always have my radii measurement, but my radius measurement is going to be determined by ultimately my function, and so I end up with f of x. So this is my setup here. Now, my f of x can be, of course, replaced because I know what my function is. My function is x cubed, and so I end up with the following as a setup. Now, this integral may or may not be easy to compute. That might just depend on, what occurs under the radical, what occurs out in front. And so it's oftentimes very important for us to understand how I would set this up as a dy question. Notice I can't change the picture, right? The picture's going to stay the same, the frustums are staying the same, everything's staying identical to what it was pictorially, but I'm just going to change the way certain things in this integral get measured. I'll start by changing the arc length measurement. Remember that if I'm going to do this, I'm going to need to change my curve to look like an x equals function. Okay, so to do this, I could go ahead and say that this would be x is equal to a y to the 1/3. And so if I was to do that, I could say, all right, the derivative then of that x would be 1/3 y to the negative 2/3. And then I could also state that I'm working in the y direction on the interval from 1 to 8. So now I've swapped over my arc length portion. My 2 pi stays the same, and now I'm interested again in swapping out whatever x to the third is. But I know what x to the third is. X to the third is y. And that's perfect because now I have an integral with all y components. And that's what I'm interested in. Now, one of these integrals is probably going to be easier than another, but if I have both of these integrals, I can determine which one I think is easier and then do the evaluation. In this case, can you maybe spot which one you think might be a bit easier to compute? Well, I would guess that it's actually going to be this first one. And I think that's pretty easy because you'll notice that underneath the radical, I'm going to have something with an x to the fourth, and on the outside of the radical, I have an x to the third, and that's a perfect setup for a u substitution. I'm actually going to leave it to you to try to go ahead and evaluate that first integral, and of course you can check the solution up online in Blackboard.